Hello everyone, welcome back. Today we're going to be looking at vectors, vector-valued functions, and especially their relationship to projectile motion. And I'll begin by assuming that you do have a working knowledge of the basics of a vector, and you should know that a vector is something that has both magnitude and direction. So when we talk about, say, velocity, which is a very important vector, we want to know what direction we're heading and how fast we're heading. How fast we're heading happens to do with speed. That's the magnitude. So magnitude is a scalar. The vector, when it includes direction, is both magnitude and direction, and that's what a vector is. So we usually write vectors with an arrowhead over the top and with brackets like this. So here is a typical vector, and we can also write it as 2i plus, actually this example is going to be minus 4j, and this is where the vector I is a unit vector in the x direction, and the vector j is a unit vector in the y direction. And so we know things like the magnitude, or the length of this vector, just by the Pythagorean theorem, is 2 squared plus minus 4 squared, which comes out to be 2 times the square root of 5. We also know that, well, let's do this on the next page. So if we keep talking about the same vector u, which is 2 comma minus 4, or 2i minus 4j, I can draw the vector, and it looks like that. And one of the things I can do also is find this little angle in here, which helps determine its direction. And that angle, if we think about this in terms of a right triangle where this is 4 and this is 2, then that angle is simply equal to the arctan of 4 over 2. And so that gives us both the magnitude. Remember, we found the magnitude to be the square root of 20 and the angle. And, just as a little bit more information, if we talk about another vector, say v, and let's say it equals 3 comma 7, then we can add these two vectors together or subtract them, same idea, and we're going to get the vector 5, 3. Right? So the big application that we have for vectors is in projectile motion. And what you want to understand is once a projectile has been launched or thrown or put out into the air, number one, its path is usually parabolic. And number two, the only force that's acting on it is gravity. And gravity is only pointing in the vertical direction, in the y direction. So here's a typical example of projectile motion. So what we're assuming is that we have some projectile, and it's being launched from 6 feet high, and it's being launched at an angle of 40 degrees with the horizontal, and its initial velocity, it's thrown with a velocity of 25 feet per second. So this represents the initial velocity of the particle. So here's what we know. We know that acceleration is always going to be acting on it, and acceleration only works in the y direction, and acceleration is minus 32 feet per second per second. So therefore the velocity, which is the antiderivative of this, is going to be some constant here, and then some other constant minus 32t. And what we'll do is we'll look over here and we'll kind of do a little mock-up of what's happening to begin with. So here's 40 degrees, and here's 25. And what we have now is kind of breaking down this vector into its components. So that's the x component, and that's the y component. And this is what we're calling C1, this is what we're calling C2. And by geometry, we are able to figure out what C1 and C2 are fairly easily. And so basically what that tells us is that the velocity vector is equal to 25 times the cos of 40 degrees, that's C1, and then C2 is 25 times the sine of 40 degrees minus 32t. So there is my velocity vector, and that's an important intermediate consideration. We'll look at the position vector on the next page. So we have the acceleration vector and the velocity vector, and therefore the position vector is going to be simply the antiderivative of the velocity vector. And so what we're going to get is 25 times the cos of 40 degrees t plus a constant, and then 25 times the sine of 40 degrees t minus 16t squared plus a constant. Now remember that our initial position was just 0, 6. That's the position when time is 0. So that tells us that C3 is 0 and C4 is 6. And so therefore that enables us to write the position vector as 25 times the cos of 40 degrees t, comma, 25 times the sine of 40 degrees t minus 16t squared plus 6. So what we have now is the acceleration vector, which in this case isn't worth that much, the velocity vector, and the position vector. And those, basically two vectors, will enable us to answer all of the interesting questions that we might be asked. So for example, to find the maximum height, we just take the y component of velocity to be 0, and that tells us when it reaches its maximum height, and we just substitute that value into the position, and that tells us how high the position, the y component of the position, and that tells us how high it goes. How about asking the question, how far downfield does it go? Well, in that case, we're going to simply take the position vector and set the y point, the y component of it, equal to 0, and that gives us the time at which it hits, and just take that time and plug it into the x component, and that'll tell us how far downfield it went. If the question is how fast is it going when it strikes the ground, well, we already found how when it strikes the ground, so all we need to do is figure out the magnitude of the velocity vector at that time. And finally, to find the total distance that it traveled, that's simply going to be the integral from a to b of the speed, which looks like that. And that'll be the same as the definite integral of the square root of the x component squared plus the y component squared. And that'll give us the total distance. And notice how similar that is to the arc length or distance of a polar curve. I'm sorry, of a parametric curve. Polar is still yet to come. So just as another example, let's suppose that we have some particle traveling with velocity given here, rather long, a little complicated, and at t equals 0, the particle is at the point 1, 5. So one question that we might want to ask is, where is it at t equal 4? So our displacement then, over the interval 0 to 4, is simply going to be the position given by the integral of velocity, the x component of velocity from 0 to 4, and the y component of velocity integrated from 0 to 4, just as before when we found displacement. And this comes out to equal 8, 16. And so at t equal 4, if it started here, then at t equal 4, the particle is at 9, 21. So now let's suppose we're asking what's the total distance that this particle traveled over the interval from 0 to 4. Well, that's simply going to equal the integral from 0 to 4 of the x component of velocity squared plus the y component of velocity squared dt. And if you use your calculator, this comes out to be about 35.5. Right, so that's a typical type of question that we deal with when we're talking about vectors. Again, there's a real similarity, a lot of crossover between vectors and parametric equations. So we'll stop here, and that means just one more topic to talk about, and that's polar equations. And then that'll finish the course. Are you as excited as I am?